In this module, we're going to learn how to analyze cost curves. So let's go. A firm has two kinds of costs. They're called fixed costs and variable costs. Fixed costs are those that don't vary with the quantity of output. So those are things like the lease on a factory. I mean, suppose you have a factory and you've got to pay a monthly lease for it. You pay that regardless of how many units of output you produce. So that would be a fixed cost. The other broad kind of cost is a variable cost, and those are costs that vary with the quantity of output. So here we're thinking about things like labor and materials. You have to use more of both of them to produce output. There are some nice pictures of some materials, coal, and some labor. The total cost curve at a competitive firm has what we call a textbook usual shape. So let me describe this. Here's a picture with the quantity of output that a firm produces, which we call Q, on the horizontal axis, and the total cost of producing that quantity of output, TC, on the vertical axis. And this is a usual shaped total firm cost curve. Well, let's talk a little bit about this. First of all, very sensibly, total costs rise with Q. It costs more to make 15 units of output than to make 10 units of output. No surprise there. But secondly, the way we've drawn it, total costs rise at an increasing rate. You notice how the slope of this total cost curve starts out shallow and becomes steeper. Now, the behavioral idea underlying this shape is that costs increase at an increasing rate because additional workers add successively less output. When you add the 10th worker, let's say he or she can produce an additional 5 units of output, whereas when you add the 11th worker, he or she produces fewer than the 10th worker produces. That's the idea of decreasing marginal product of labor. That's a little bit under the hood for our purpose, but the point is we're going to think of total cost curves at competitive firms having this usual shape, upward sloping at an increasing rate. And again, the behavioral idea underlying it is this idea of declining marginal product of labor. Notice one more thing before we move on. This firm has costs even when it produces no units of output. Notice that when Q is 0, that the total cost is 100. That 100 here is the fixed costs. They're present regardless of how much output is produced. Let's introduce a new idea, an idea called marginal cost. Marginal cost is the change in total cost within an additional unit of output. So if we go back to our usual shaped total firm cost curve, let's consider two quantities of output that I've labeled A and B in this picture. So if you want to see marginal cost at quantity A, what you want to look at is the slope of the total cost curve at A, because marginal cost is the change in total cost with an additional unit of output. So we could draw a line up from A to the total cost curve and then ask, hey, what's the slope of the total cost curve at that point? And I'm trying to illustrate that slope with this long tangent line. At B, we could also draw a line up from B to the total cost curve and say, hey, what's the slope of the total cost curve at the quantity B? And that would be this tangent line, the slope of this tangent line that's tangent at the point where B is on the total cost curve. So the marginal cost at quantity B is the slope of the total cost curve at B. Now, one thing to note, with our usual shaped total cost curve, the marginal cost is rising as the quantity rises. So that is to say the slope of the total cost curve at A is lower than the slope of the total cost curve at B. So that means, or I should say that's going to result in the following: with the usual shaped total cost curve, marginal cost is going to look like this. It's rising, and moreover, with the functions we'll use in this course, it'll be a straight line. One further thing to note, it doesn't necessarily go through 0. In fact, here it doesn't actually go through 0 at all, but we'll see some examples down the road, so we'll go into more depth on that shortly. Let's introduce another idea, the idea of average cost, which we call AC. Well, average cost is the total cost of producing Q units of output divided by Q, or in the words here, total cost divided by the number of units of output. To get an idea about this and to see how it works, let's think about a quantity like 5. At a quantity of 5, AC is the total cost of producing 5 units divided by 5. Now in this diagram, we can see this total cost of producing 5 units is this vertical distance indicated by the bracket above the number 5, and the total quantity produced is, of course, 5 units. Now one thing to note that's kind of handy for us is that we can illustrate average cost as the slope of a ray from the origin to the total cost of producing any particular quantity. Note here that I've drawn a ray from the origin, that is the point where it's 0 on the quantity axis and 0 on the total cost axis. So we have this ray running from that origin to the point along the total cost curve associated with producing 5 units of output. Now slope is rise over run, so that means the slope of that ray is TC of 5 divided by 5, which is exactly the average cost of producing 5 units. So what can we say about average cost? Well, it starts out high because if we draw a ray from the origin to a point that's sort of not too far along the average cost curve, the slope's pretty high, and then the slope falls. In fact, it falls and it reaches a minimum because if you think about drawing rays from the origin, the one you see here, the second one, is the lowest slope ray that's actually going to touch this total cost curve. And so after that quantity, which is about 10, average cost is going to start to rise. So just think about the slopes of the rays from the origin to points along the total cost curve. They start out with high slope, they reach a minimum slope, and then the slopes rise again. The consequence of that is that the average cost curve is U-shaped. It starts high, it falls, reaches a minimum, and then rises again. Another point I want to make is that marginal cost is going to cross average cost at the minimum of average cost. That's kind of a mouthful, so let's see if we can talk through it. Well, let's think back to what we just learned. First, marginal cost is the slope of total cost, and that's true at any quantity. Second, average cost is the slope of a ray from the origin to any point along the total cost curve. So there's something special about that point A, that quantity A, which you may recall was the minimum. It's going to be the quantity with the minimum average cost. What's true about that point is that at A, marginal cost equals average cost. Because this is the quantity where AC is lowest, and so MC crosses AC at the minimum of AC. Let me just say it one more way, because this is often a bit confusing. Think about that tangent line that's tangent to the total cost of producing A units of output. Well, that tangent line has two special things going for it. One, since it's a tangent line, it shows the marginal cost at A, but it happens also to be the ray that goes through the origin. So it's both the marginal cost of producing A and the average cost of producing A. Furthermore, it's the tangent line that from the origin, and so it's the minimum average cost. One more definition for us, average variable cost, AVC. It's the variable cost divided by units of output. So think back, we found that with this particular total cost curve, the fixed costs were 100. That means that the distance above 100 in the total cost direction is the variable cost. So think about a quantity like the quantity A here. If you were to go straight up from A to the total cost curve, that would be the total cost of producing A. But the first 100 is just the fixed cost, so the remainder is the variable cost. Well, average variable cost is the variable cost divided by the number of units of output. So in this case, the average variable cost of producing A units of output is that VC of A divided by A. And we can represent average variable cost by the slope of a ray or a line from, not from the origin, but rather now from 0, FC. So here in this diagram, that's 0 along the quantity axis and 100 along the total cost axis. So a ray from that point to any point on the total cost curve. And again, the slope of that ray is the average variable cost. One thing to note and this is not surprising, is that the average cost is higher than the average variable cost. Well, you can see that two ways. One way, no diagram needed at all. Just remember that average cost has fixed costs in it as well as variable costs, so of course it's going to be bigger. But the second way to see it is with our little kind of slope argument. The average cost of producing A is the slope of a ray from the origin up to the total cost of A. The average variable cost is the slope of a ray from that 0, FC point, 0, 100, up to the total cost line. And of course, that higher ray has lower slope than the average cost ray, and so the average variable cost is lower than the average cost. Now, with our usual shape, the average variable cost is going to rise. And indeed, with the function we typically use in this class, it doesn't just rise, but it's also a straight line. But it's also a straight line. Now, if we put average cost and average variable cost and marginal cost together, we get a picture that looks like this. This picture is good to dwell on for a minute because it's kind of handy. We'll use it a bit. So what's going on here? We've got that U-shaped average cost curve. We've got marginal cost that's here a straight line and that rises and comes through the minimum of average cost. And then we have average variable cost, that lower straight line. And notice that average cost converges toward average variable cost. Why is that? Well, the difference between them is fixed cost divided by quantity. And as some fixed cost gets divided by larger and larger quantities, that FC over Q becomes smaller and smaller. So eventually, at an infinite quantity, kind of implausible, they would actually touch. Now, one way to get real clarity about these is to work with an example. So let's do that for a couple of slides. So how do we work with these cost curves? Well, here's an example, a particular function. Let's say that the total cost equals 100 plus 10 times Q plus Q squared. Now, in this class, I would also give you the marginal cost curve. So it turns out that the marginal cost curve associated with this total cost curve is MC equals 10 plus 2Q. Just a little aside here, if you happen to be a calculus buff, you would maybe want to note that marginal cost is the derivative of the total cost with respect to quantity. But if you're not a calculus buff, that's okay. This class doesn't require it. It's just that folks who already know that sometimes get frustrated if I don't mention it. So there, I've mentioned it. Anyways, we can ask some questions about this total cost curve, this particular function. Like, first of all, does it behave according to the so-called usual shape that we've articulated? Well, there are a couple ways to see this. One is just to make a little table with Q in the first column. Here we're to look at the quantities 0, 5, and 10, and then just solve for the total costs associated with those quantities and think, does this thing seem to have that usual shape? So at a quantity of 0, the total cost is 100 because it's TC equals 100 plus 10 times 0 plus 0 squared. At a quantity of 5, it's going to be 175, but let's talk about that for a second. That's 100 plus 10 times 5, which is 50, plus 5 squared, which is 25. So yeah, that's 175. At a quantity of 10, it's 300. Why is that? Well, it's 100 plus 10 times 10, or 100, plus 10 squared, which is another 100. Now, before we look at the picture, let's just think about what's going on here. As we go from 0 to 5 units of output, total cost goes from 100 to 175. So total costs rise by 75. As we produce another 5 units of output, going from 5 units to 10, how much would we expect costs to rise if we had a usual shaped curve? Well, by more than 75, because remember, costs are increasing at an increasing rate, and sure enough, that's what we see here. The additional cost of those next 5 units of output is 300 minus 175, or 125. So yes, indeed, if we plot this out, and we'll let Excel do it for us, but there it is. It starts at an intercept of 100 on the TC axis, and it rises at an increasing rate. So indeed, this function gives us a usual shaped cost curve for the purposes of this course. Next, let's find fixed costs. Maybe this would be clear since we've kind of already talked about it, but again, we're using the same total cost curve. Fixed costs, by our definition before, is the part that doesn't depend on Q. If you look at that total cost function, well, there's 100, and then there's a 10 times Q, and then there's a Q squared, and those last two terms certainly do depend on Q, but the first one doesn't. So the fixed costs for this function is 100. How about average variable costs? Well, average variable costs is total costs minus fixed costs over quantity. Or we could have just said it's variable costs over quantity, but of course variable costs are total costs less fixed costs, so this is true too. In this example, so let's write it out, it's 100 plus 10 times Q plus Q squared, and that first chunk was total costs. But then let's subtract off the fixed component. And so that's why I've struck through the 100 both times, because they cancel. All that stuff's being divided by Q. If we simplify a bit, we have 10Q plus Q squared all over Q. And if we simplify that further, we end up with 10 plus Q. What does that look like? It's a straight line, and it starts at an intercept of 10 on the AVC axis and rises with, in this case, a slope of 1. So indeed, this is what we said. We expected a straight line, not necessarily with an intercept of 0. How about average costs? Average costs are total costs divided by quantity. So here we have 100 plus 10Q plus Q squared all divided by Q. Now this one doesn't simplify to something quite so simple. The first term is 100 over Q, and plus 10 plus Q. So you might note here that what we've got going on in this last part of the equation is we've got average variable cost plus 100 over Q. 100 over Q is fixed costs over Q. When we make a picture, though, this thing's not a straight line. This thing is, well, U-shaped. Starts high, falls, reaches a minimum, and then rises again. Now let's put them all together. We put them all together using the information we've derived in the previous couple of slides. We have the following equations of MC and AC and AVC. And we have a picture that looks as this picture looks. We have U-shaped average cost. We have marginal cost rising through the minimum of average cost. And we have average variable cost rising and kind of converging toward average cost. One final thing we could do is we could find the quantity where MC crosses AC. And in so doing, we'd also be finding the minimum, the quantity where we have a minimum average cost. How would we do that? Well, we could just go ahead and do what's in this little parentheses at the bottom right of the slide, solve the equation that sets marginal cost, 10 plus 2Q, equal to average cost, 100 over Q plus 10 plus Q. I'll leave that as an exercise for you, but it's not too hard, and you can see that Q min AC is equal to 10. It's also illustrated in the picture. If you look straight up above that quantity 10 on the quantity axis, yep, indeed, that gray marginal cost line is crossing average cost at the min of average cost. Let's do some takeaways. What did we learn in this module, which was really pretty nuts and boltsy? We learned the following things. Total cost equals fixed costs plus variable costs. Fixed costs are the costs that do not vary with output, while variable costs are those that do. We learned that average cost equals total cost over quantity, and for us it'll be a U-shaped curve. We learned that average variable costs are variable costs divided by the quantity of output, and for us it'll be a straight line. Marginal cost is the cost of producing an additional unit of output. It's also the slope of the total cost curve. And finally, we saw that marginal cost equals average cost at the minimum of average cost. This stuff's going to be really useful for us as we go on and analyze all kinds of interesting problems.